So, what we see here is the cardiac output equation. You're going to see Q is going to be cardiac output, and the formula for that is heart rate times stroke volume. And so, we're going to see a couple factors that affect this formula. So for heart rate, you're going to see the nerves kind of affect the heart rate. You're going to see such as like the accelerator nerve. The accelerator nerve works to increase heart rate. The vagal nerve works to decrease heart rate. And also, heart rate is going to be affected by hormones, such as epinephrine and norepinephrine. These kind of coexist together in a way where epinephrine is released and then stimulates the accelerator nerve to increase heart rate. Norepinephrine is going to do the opposite. It's going to stimulate the vagal nerve and decrease heart rate. Stroke volume has three factors as well that helps influence if it goes up or if it goes down. So what you have here is you have preload is effective for stroke volume. What preload is basically end diastolic volume. That is the amount of blood that can fill up in the ventricles before it is pumped. And a way to increase that is through venous return. Venous return basically means just how much blood is just coming through and back into the heart efficiently. And so what you see with an increase of end diastolic volume, you'll see an increase of strength of contractility. This is known as the Frank-Starling mechanism. Frank-Starling mechanism, to simply put, is just the bigger the stretch, the bigger the squeeze. If you can get more blood in your ventricles, you can produce more strength of contractility in your heart and pump better and increasing your stroke volume. So, you also have, again, that's contractility. This is due to like epinephrine. Again, we'll look later at a chart, at this chart more specifically, about how that affects it. And then we have afterload, which is just the back pressure that is being placed on the aorta this way. So blood, it's basically pressure that pushes against the valve. And the higher it is, the harder it is for blood to come and pump out of the heart. And this can be regulated by vascular tone. If we can dilate the blood vessels, we can decrease blood pressure out here and make the back pressure on the aorta lower. So, looking at this chart, we're going to see kind of an easier way to see the correlation of everything. So we see cardiac output. If we see an increase in heart rate, you're going to see an increase in cardiac output. We'll start from the bottom. We'll see heart rate is affected by the sympathetic system, mainly epinephrine. That's going to increase the heart rate. It's also going to help increase venous return since the blood is pumping so much faster and it's pumping more blood. Epinephrine also causes an increase of strength of contractility. The stronger it pumps, the more blood you can get out the system, the stronger the stroke volume, which increases cardiac output as well. If you look as well, you'll see venous return has correlation with the end diastolic volume, as we remember is the blood that fills the ventricles before the squeeze. What you're going to see here is that with this, remember the Frank-Starling mechanism, we can increase that with the bigger the stretch, the bigger the squeeze, and then we see a positive correlation of strength and contractility, which again can increase stroke volume. So how does exercise play into this? Well, during exercise, your body is going to need to find a way to get oxygen into those target muscle groups that are working, because those muscles are going through the energy systems much faster than usual, and so therefore they're going to require more oxygen. So with that, you're going to see in exercise an increase in heart rate, and this is going to be due to the sympathetic system. Sympathetic system is going to release epinephrine, which increases heart rate. So we'll see that exercise affects the variable of heart rate, and we'll also see how it affects stroke volume. Again, the reason why it affects stroke volume is because you can see the correlation with the sympathetic system and the epinephrine. Increasing the strength of contractility increases the stroke volume. So you'll see how exercise also affects the stroke volume. So with that being said, the reason why our heart rate is raised is because we're trying to pump that blood down and into the target muscle groups in that area. And the way we can kind of guide it is through like vascular toning. We're going to see more dilation in areas of the muscle that are needed and more constriction of the muscles that aren't needed. This is kind of a way for, like, as we remember, the going down the pressure gradient. If the blood sees an area of lower pressure, it's going to want to work its way there for more room. So now that we can understand how the blood needs to get there, we need to know the whole cycle throughout the heart, and it's basically the direction it takes in order to get that blood delivered where it needs to be. So what you're going to see here is superior vena cava, and the inferior vena cava is going to bring in deoxygenated blood. It's going to enter through the right atrium and down to the right ventricle. That blood is then going to be pumped throughout the pulmonary valve. It's going to be sent up down to the lungs, and where you're going to see a CO2 drop off and oxygen pickup. So those blood cells are going to pick up oxygen and become reoxygenated again, and they're ready to go. They're ready to be delivered wherever they need to be. So that blood is then going to come back to the left atrium and down into the left ventricle. That left ventricle is then going to really squeeze and contract, and it's going to work its way up to the aorta. And throughout the aorta is throughout the highway of the whole body. So it's going to work and finally get that blood out to where it needs to be. And in order for us to know how this works, we can actually see an electrical viewpoint where, like, we can see the impulses of how this contraction works. So what we see here is the SA node. The SA node is going to work and depolarize. It's just a bundle of nerves. Work to depolarize in its direction down throughout the atrium. Not as any specific atrium, just both. It's going to reach this layer of inert cells, and that's when it detects from the AV node. So the AV node is going to then depolarize. It's going to go down the bundle branches and up the Purkinje fibers, almost in a uniform direction because it needs to squeeze up. See how we go up and up to the aorta to deliver throughout the body. And you can actually see this on the EKG of, like, in hospitals. Basically what happens is you see a bump, a huge bump, and then a smaller bump again. And then you have the P wave. The P wave is going to be atrial depolarization. That's where you're going to see this occur. The QRS complex is going to be a much bigger bump, is because you're seeing a ventricular depolarization. This is also going to be where atrial repolarization is, but you're not going to see that because the ventricular depolarization is occurring, and the reason why it's so much bigger is because this ventricle really needs to work really hard to squeeze and send nerve impulses to send that blood throughout the whole body, whereas the atrium just works on bringing blood into the ventricles. So you see why that makes a difference. And then lastly, you have the T wave. The T wave, again, is just going to be ventricular depolarization, which allows these ventricular chambers to rest. And that's basically what the EKG is showing this throughout this whole time. And that's why this blood is able to go out throughout this whole way in this certain direction because of those electrical impulses. And basically, to sum it all up, that is why exercise is able to manipulate both variables of cardiac output, with heart rate just being it's increasing because of the sympathetic nervous system, which releases epinephrine. And in turn, with correlation, is it increases strength of contractility. And obviously, we see that affects the stroke volume. And doing so, it increases cardiac output. So we basically see exercise increases cardiac output. And the big reason why is because it needs that blood to be delivering oxygen to those target muscle groups that are working really hard in order for it to keeping it from fatiguing.